When a private eye in a rain-hammered city wants to unravel a web of crime and corruption, they often have one mantra: follow the money. In a trail of dollar signs, ones and zeros, provided they are dogged enough, they usually find the perpetrator. When it comes to the planet Mars, scientists have a different mantra: follow the water. The case they're trying to crack is one of the coldest cases on the books, one that has baffled investigators for hundreds, if not thousands of years. Did life ever arise on Mars? And like all good investigations, it's all about collecting the right evidence. If water did once flow on Mars, signatures of life could be found in its sediments. Find the water, potentially find signs of life. It's a good thing then that science has set to work detective with steel in their hearts, who rarely sleep, and whose memories are literally photographic. Rovers. And today we're going to look at the times they blew this water case wide open. I'm Alex McColgan and you're watching Astrum. Join me in this gritty supercut, because Mars is covered in a lot of grit. For the moment, Mars rovers have proven once and for all that water used to flow on the Martian surface. It's quite the story. Just don't expect a femme fatale. There have been 6 successful rover missions on Mars, but of those we're going to focus on 3. NASA's Opportunity and Perseverance rovers, and China's Zhurong. So let's take a closer look at the first of our 3 rovers, going back to about halfway through its mission.
The date is the 15th of December 2010. 2,449 souls into Opportunity's mission to find evidence of past oceans on Mars. Up until this point, Opportunity had travelled over 25 kilometers, investigating rocks, craters and bedrock, while traversing sand dunes and plains. The areas it had explored so far contained clues that suggested that these areas were regularly flooded by water, although it fell short of confirming that a constant body of water was present there, like an ocean.
Opportunity was now looking for something more definitive.
Mars's harsh environment had also started to take a toll on Opportunity, with some onboard motors failing, meaning it couldn't stow its robotic arm away anymore. Our persevering champion had just arrived at Santa Maria crater, but for scientists, the most exciting prospect for the mission was finally on the horizon, a big 22-kilometer crater where clays had been detected by the Mars Reconnaissance Orbiter. Clays are significant because they are hydrated minerals, meaning surface water was likely to have pooled there for lengthy periods of time. After spending 3 fairly uneventful months at the Santa Maria crater, Opportunity headed towards the closest hill on the crater rim, known as Cape York. Along the way, it came across a few small craters, some of which were very young, with ejecta from the impact strewn across the place. But Opportunity didn't stay for long.
Approaching Endeavour, that's the name of the crater,
Opportunity was finally able to see some variation in the landscape after years of simply crossing flat plains of sand dunes. Peaks and capes started to rise up on the horizon as Opportunity approached the crater rim. On Sol 2709, Opportunity finally arrived at Cape York, and specifically a place known as Spirit Point, named after Opportunity's sister rover that had come to the end of its mission on the other side of the planet only a few months previously. Opportunity had travelled over 30 kilometers up until this point, 50 times further than the original planned mission distance. Mission planners decided not to go into the crater, as points of interest were again found around the rim of the crater. Bedrock is exposed to the surface there, which allowed Opportunity to study the oldest rocks it had seen so far on this journey. It was also around these peaks and capes along the rim where the hydrated minerals or clays were detected by the MRO. Perched on top of Spirit Point, Opportunity looked over Endeavour, providing a perspective about just how big this crater is. From the onset, Opportunity began discovering phenomena never before seen on Mars.
The soil found around the areas Opportunity had thus far explored contained countless smooth, tiny round rocks, nicknamed blueberries, strange geological formations that have thus far defied scientific explanation, though we think they may hint at a watery past. However, around Endeavour, no blueberries were to be found.
Instead, the soil looks much coarser, the rock sharper and not as rounded. Mission controllers were so impressed by the variation of this area compared to the initial landing site that they said that this section of the mission provided the equivalent of a second landing site for the price of one. The first point of interest Opportunity examined was a large ejector rock called Tisdale 2. It was unlike any other rock so far examined on Mars. It had volcanic characteristics, but contained more zinc and bromine than previously seen. It was determined to be a type of breccia, old rock fragments having been fused together. This was further evidence for water. The impact that threw this bit of ejector likely released hot underground water that deposited zinc in the rock. Just a short distance from Tisdale 2, Opportunity discovered perhaps the most conclusive evidence that water existed on Mars thus far. Can you guess what it is from this picture? Look closely at the bottom of this image and you'll see a thin white line exposed in this outcrop. A close-up examination of the vein revealed it to be gypsum, the alpha particle X-ray spectrometer on the rover's arm detecting the minerals calcium and sulfur, together making calcium sulfate. They named this vein the Homestake deposit, and it likely formed from water dissolving calcium out of volcanic rocks, which combined with sulfur and was then deposited as calcium sulfate into an underground fracture that later became exposed at the surface. The impact that threw Tisdale 2 likely had something to do with this vein as well. If this is the case, it shows that water once flowed through underground fractures on Mars. Later analysis of the data Opportunity collected showed that not only was this likely to be gypsum, but also that the water here would have been much less acidic than it would have been around other locations on the planet, meaning it could have been more conducive to life. Martian winter was soon setting in, meaning shorter days and a lower sun in the sky. For a solar-powered rover that can't adjust the angle of its solar panels, this is not the ideal situation, but for the first time since the mission began, Opportunity had the opportunity to spend the winter on a slope aimed towards the sun, meaning that for this winter it would be confined to an area named Greeley Haven. This area was not only aimed towards the sun, but it was also rocky, meaning Opportunity had a lot it could examine during these few months. This 360-degree panorama shows the tracks of Opportunity as it carefully navigated its way to its winter lodgings. Months had passed, and winter was turning again to summer. On Sol 2947, Opportunity moved again for the first time since it set up camp in Greeley Haven. Luckily, everything that was functioning from before seemed to still be functioning, and Opportunity headed out to the next point of interest. MOR data suggested clays were present in this area, and the mission team were determined to find it. A beckoning outcrop was spotted around Sol 3057, and the microscopic camera revealed something about it that no one was expecting. Much like Opportunity's landing site, these smooth polished blueberry rocks were observed. However, this time they were very much a part of the rock. They were also smaller than what Opportunity had seen before, only a few millimeters in diameter, and not rich in iron like the landing site blueberries. A few of the exposed blueberries observed had been eroded away, revealing their internal structure. Scientists describe these blueberries as crunchy on the outside and softer in the middle. They are different in concentration, they are different in structure, they are different in composition, they are different in distribution. It was quite the mystery. Opportunity had just one more place to visit on its trip around Cape York, and that was the clay patch dubbed Whitewater Lake. On its way there, the Earth and Mars were just going through a phase called solar conjunction, where Mars is behind the Sun, which blocks communications between mission controllers and the rover. This has happened a few times during the course of the mission already, but this time Opportunity gave mission controllers a bit of a scare, as during the communications blackout, Opportunity's onboard computer reset into standby mode. Thankfully, communications were restored, Opportunity booted back up properly, and it carried on to Whitewater Lake. And it was there Opportunity discovered Esperance, the pale rock in the upper center of this image, which is about the size of a human forearm. This was it, the treasure scientists had been looking for. Esperance's composition was found to be higher in aluminium and silica, and lower in calcium and iron, more so than any other rock Opportunity had examined in more than 9 years on Mars. Testing found that this rock had a clay mineral content due to intense alteration by water. Opportunity spent weeks here, making sure the measurements were correct, getting everything it could get done before Martian winter came around again. Opportunity left Cape York on Sol 3344, having spent 9 Earth years, or 5 Martian years, on Mars's surface. They found the best evidence out of any Mars mission that neutral pH water once existed on Mars.
But scientists were not content to let the mystery end there. To get a clear idea of where water, and thus potential life, had once resided on Mars, other locations on the dusty surface needed to be explored. As such, in 2021, our next rover was sent to locations within a crater known as Jezero, thousands of kilometers away.
In Jezero crater, there is a dune field known as Saita. In amongst these dunes, there is a series of outcroppings that were of particular interest to Perseverance's mission, due to the many different layers of exposed rock they gave access to. These different layers likely represented different geological eras, which would give scientists the clearest picture of the history of Jezero, as well as giving them an opportunity to find life itself. Outcroppings are of particular interest because Perseverance's drilling equipment only allows it to dig several centimeters deep. If it wasn't for outcroppings, where erosion had exposed these layers to the Martian atmosphere, Perseverance would not have access to them. However, sand dunes are of particular danger to a rover like Perseverance. With help an entire solar system away, if Perseverance was to start wheel spinning in a section of particularly loose dune, it would likely spell the end of its mission, much like it did for the Spirit rover in 2009.
As such, Perseverance's trusty sidekick, Ingenuity, a small helicopter, the first of its kind on the Martian surface that had traveled to Mars along with Perseverance,
was sent in to conduct some preliminary reconnaissance. If it could find a route through the sand dunes that looked safe, Perseverance could get its sample tubes to the vital outcroppings of Saita. Ingenuity began its scouting before the solar conjunction and flew for several flights
from September through to December 2021.
Flying at a height of 10 meters, these reconnaissance expeditions allowed scientists to pick out the perfect route. Perseverance set off in early November 2021, beginning its exploration of the dunes. It picked its way carefully, being sure not to travel too fast in case it fell into any unforeseen sand trap. It moved between dunes that were a meter high, finding the flattest path. But thankfully, Ingenuity had led it true. Perseverance was able to make it to the protruding rock known as Brack.
By now, Perseverance had had time to practice drilling into Martian rock with its coring drill. Some of this successful, and some not so. But either way, now that it had its technique down, Perseverance quickly was able to obtain new samples.
Deciding to call the first empty sample container at Brack an atmosphere sample, these next 2 samples were officially Perseverance's 5th and 6th sample tubes and their 3rd and 4th rock samples. From these accumulated samples, scientists were able to make an unexpected discovery. These were not sedimentary rocks, as had first been anticipated. Instead, Perseverance had discovered the igneous rock, Olivine. Olivine is a type of rock that can actually be found here on Earth, for instance in parts of Australia. Unlike sedimentary rocks, which are made by particles of sand and other detritus slowly accumulating on top of each other over time, an igneous rock like Olivine is formed by the cooling of magma. As such, it seems that at one time or another, Jezero crater must have been witness to some volcanic activity. While this might initially seem to be bad news, you might correctly conclude that not much life could be found in magma. Scientists could discern signs of water erosion on the rocks. The ridges at the ends of the crater showed signs of water motion. Whatever volcanic activity had happened here, the water that created Jezero's delta must have come after it had already cooled. As such, the presence of igneous rocks was actually good news. Igneous rock is usually very high in minerals. This is why the areas around volcanoes are so fertile. The presence of water and high mineral count rocks could have been the perfect conditions for life.
In the future, scientists will be able to send missions to locations like the Jezero crater delta as they make future attempts to locate alien life. Indeed, once humans land on Mars as is planned for the 2030s, it's not unimaginable that archaeological dig sites will be one day set up in locations like this, with humans in spacesuits gently brushing away the fine oxidized iron and basalt rock to see if signs of life can be found underneath. But still, scientists yearned for clearer pictures of Mars's ancient waterscapes than this, and it was now likely that water had pooled in craters and flowed in rivers. But what about the step beyond that? Could ancient Mars have once housed oceans? If true, this would be exciting for those searching for signs of ancient alien life. A shoreline could have supported an abundance of life, possibly entire diverse ecosystems.
And they might have left behind biosignatures, like scavenger hunt clues we can use to paint a picture of Mars's ancient coastal habitats. Shore environments offer key advantages to budding life. They concentrate organic molecules through evaporation, promote the formation of complex molecules like RNA and protein, and provide mineral-rich surfaces and energy sources like UV radiation, heat, and chemical gradients, all of which can drive the chemistry needed for life to arise. In contrast, rivers are too dynamic and dilute to support the delicate chemical conditions needed for life to arise. They constantly flush materials downstream, making it difficult for molecules to accumulate and react the way they need to form life. So if researchers could find evidence of a standing body of water on Mars, like a lake or an ocean, they'd be in a much better spot to search for remnants of microbial life.
The Chinese Tianwen-1 mission might have captured the most compelling evidence yet for ancient oceans on Mars.
It's the first on-the-ground data ever collected of a suspected ocean zone, and it makes a strong case that our shoreline theory is on the right track. On the 23rd of July 2020, the Tianwen-1 spacecraft began its 202-day journey to Mars. Aboard, it carried an orbiter, lander, and the Zhurong Rover. The aim of the mission was to investigate Mars's geology, climate, and habitability through three key activities. By studying the surface and subsurface of the Utopia Planitia, a region scientists think could be an ancient ocean basin based on mapping from satellite data. By performing climate and weather monitoring, including magnetic field variations and dust activity's effect on solar panels and climate. And by searching for signs of water and habitability, investigating whether the region harbored conditions suitable for life in the past. On the 10th of February 2021, Tianwen-1 entered into orbit around Mars. Controllers spent 3 months testing the probe systems, shifting its orbital path from equatorial to polar, and preparing it for its main science mission. Finally, on the 14th of May, the lander touched down on the Red Planet, and a week later, the Zhurong Rover was successfully deployed, making China only the second nation in history to successfully deploy a rover on Mars, behind the USA. For China, this mission represented more than just scientific discovery. It showcased their spaceflight capabilities and autonomy, and demonstrated they can launch and operate missions without relying on foreign navigation or communication systems. The Tianwen mission, meaning questions to heaven, laid the foundation for future Chinese missions like a Mars sample return and a possible crewed mission to Mars by 2033. The 240-kilogram rover was deployed in a region of Mars known as Utopia Planitia, the largest known impact basin in the whole solar system. It's the same region where the NASA Viking missions landed almost 50 years ago, but recently interest in this area was revived due to a 2016 NASA discovery. Turns out, it is home to a massive amount of underground ice, about as much water as you'd find in Lake Superior, about 12,100 kilometers cubed, or 1 × 10⁻16 liters. So, to study this promising region, the Zhurong Rover came equipped with 13 different scientific payloads, which can be thought of as 4 categories. Radars, to detect subsurface structures up to 100 meters underground, including the ground-penetrating Roper radar. Spectrometers, to analyze soil and rock compositions, including a laser-induced breakdown and infrared spectrometer. Optical cameras that will image the planet from both the orbiter and the rover, as well as provide topography and navigation capabilities, and monitors for atmosphere and space environments that will detect the magnetic field, space radiation, and the climate of Mars, including a surface magnetometer and the Mars Climate Station, designed to monitor local temperature, wind, pressure, and even record sound. The rover also carried a deployable wireless selfie camera that produced some of the mission's most iconic images, like these. So, loaded up with all these scientific payloads, what exactly did Zhurong discover about the Martian coastline that past missions had missed? To fully understand this, we need a quick geography lesson. On Earth, sediment particles are transported by wind, water, and ice, carried through rivers, or moved downhill by glaciers. This sediment is eventually deposited in low-energy environments like river deltas, lake and ocean floors, floodplains, and the base of hills or mountains. But it can also happen along coastlines, more specifically along the part of the beach known as the foreshore. This is a dynamic part of the shoreline between the high tide and low tide lines. Here, sediment can be added or removed depending on things like wind, tides, weather events, and the type and size of sediment particles. On Earth, the foreshore zone tends to slope gently towards the sea. The gradient of the slope depends on the type of sediment. For example, beaches made of smaller, finer particles result in low gradient beaches, while beaches with cobbles may be stacked as steep as 20 degrees. These sloping layers record the long-term balance between sediment supply, wave energy, and water level, and can be preserved in the geological record for millions of years. Back on Mars, the Zhurong Rover was hard at work studying the planet's subsurface topography. It did this by sending radio waves into the ground using its Roper radar. When the radio wave hits a boundary between 2 different materials, for example, when the composition shifts from fine-grained sediment to coarser sand, the signal bounces back. This creates a reflector in the radar image. What grabbed the Zhurong's team's attention was not just that signals were bouncing back, but the angle they were bouncing back at. All 76 of the geological reflectors they encountered sloped in the same direction at an angle between 6 and 20 degrees. Putting the pieces together, the team realized that 10 to 35 meters below the planet's surface lies a 1.3 kilometer stretch of terrain sloping towards the lowlands. It seemed like more than coincidence. Could this be proof of what they were looking for? The indisputable evidence for an ancient shoreline on Mars. The team hurried to compare this Martian picture to the buried beaches found on Earth, and found the Bay of Bengal to be such a strikingly similar Earth analog, they even featured this finding in their paper. One of the co-authors of the original research paper that published the findings said, "It's a simple structure, but it tells you there had to be waves. There had to be a nearby river supplying sediment, and all these things had to be active for some extended period of time." We also know that the Sun and Mars's bigger moon, Phobos, do affect the planet's surface gravity, which could have caused tides on the ancient ocean. The team briefly considered, but ultimately ruled out other possible explanations for the sloping structures. They argued both sand dunes and lava flows would lead to slopes pointing in multiple directions, yet in the Zhurong data, all the reflectors point the same way. They concluded that these slopes were more consistent with a coastal foreshore environment, strengthening the case that Mars once had dynamic shorelines that experienced tides, wind, and waves, just like Earth does today. For decades, scientists have been locked in heated debate over the question of Mars's oceans. The evidence seemed frustratingly unclear. Prominent researchers dismissed shoreline evidence as artifacts or poor image resolution, and climate modelers struggled to explain how liquid water could exist on an early Mars with a fainter sun. You see, 3.5 billion years ago, our sun was about 25% dimmer than it is now, too faint to keep Mars above freezing. And yet, our climate models predict that at the time, Mars would have been covered in rivers, lakes, and even oceans. This leads to what is known as the faint young sun paradox. If the heat for liquid water didn't come from the sun, it must have come from Mars's atmosphere. This has led to three theories trying to solve the faint young sun paradox. The first says Mars was warm and wet. The idea is that Mars's atmosphere was loaded with greenhouse gases, mainly carbon dioxide and water vapor, which made it so dense it could trap enough heat to allow liquid water to persist for millions of years. This would explain the evidence pointing to rainfall, lakes, and oceans. But the problem is, according to our models, carbon dioxide and water vapor alone can't produce the warming needed for this scenario. Other gases like methane, ammonia, or hydrogen would be needed, but they are unstable and hard to maintain long term. The second possibility is that Mars was only warm and wet some of the time, mainly in response to major events like massive volcanic eruptions or asteroid impacts. These could release huge amounts of heat or greenhouse gases, creating long-lived warm spells where ice melted, rivers flowed, and erosion occurred. But we can't know for sure if the intensity and frequency of these spells would have been enough to carve all the valleys and fill the lakes we see evidence for today. And finally, some think Mars spent most of its history as a frozen ball. Landscapes were dominated by snow and ice, but under certain conditions, like changes in Mars's orbit or sudden heating events, the ice melted. This explains why Mars shows signs of both glacier activity and flowing water. But what could have melted all that ice often enough for the erosion we see to occur? None of these three scenarios perfectly explain Mars's past climate. Frustratingly, despite the strong evidence for shorelines, we still don't know how to reframe our models of Mars's early climate to allow for water to persist there.
Although a paper released in the journal Communications, Earth and Environment in December 2025 found evidence in Perseverance's data that suggested clays it saw had been sculpted by consistent, heavy rain, lending weight to one of the rainfall options. Still, solving the faint young sun paradox may be the key to understanding whether Mars was ever truly habitable. So it's too soon to get carried away imagining some billionaire digging up Martian beaches and turning them into resorts. The truth is, we still need more data to put the full puzzle together. Tragically, even in the best investigation cases, evidence can go missing. Perseverance spent much of its time on Mars collecting samples for a future retrieval mission in 2027 or 2028, with a return scheduled or the late 2030s. This would have given us more clarity into the planet's complex and ancient geology, and perhaps closed the debate for good. But then, NASA was threatened with massive budget cuts in 2025, and while Congress passed a bill in early 2026 that secured NASA's funding, Perseverance's sample return mission was the one exception. Those clues to water conditions on ancient Mars, and one sample that NASA described as the clearest sign of life ever found on the red planet, will remain trapped on a world tens of millions of kilometers away from our own. It may be up to humans who might one day live on Mars to walk over there and pick them up, if we are to find out the secrets those samples contain.
Even though Zhurong was only designed to last 93 Earth days, it persisted well beyond this timeline, collecting data for an impressive 358 days until it went dormant on the 20th of May 2022. With appropriate temperature and sunlight conditions, Zhurong was expected to wake up in December 2022, but never did, due to excess dust accumulation. As we look to the future, more questions remain to be answered. If Mars had stable oceans for millions of years, what happened to all that water? How did the planet transition from a potentially habitable world to the frozen desert we see today? Could a similar fate await Earth? And if life did emerge in these ancient coastal environments, could traces of it still exist, buried beneath the surface?
Our metal detectives might have enabled scientists to follow the water, but the suspected existence of fossilized life itself on Mars is a case to solve for another day.
Thanks for watching. We mention this a lot, but that's only because it genuinely makes a difference. Astrum runs because of people like you who take a moment to join us in what we do. So consider taking 1 minute to look at the Astrum Patreon and see if any of the tiers and rewards interest you. Every member is core to our videos, and you get to watch all of these videos completely ad-free. We truly couldn't make these videos without you. If you enjoy what we do, come join the Astrum community today.